Good afternoon. I'm Alex Kurapov at NOAA, Silver Spring, Maryland. So we are a coastal ocean modeler who started to look at bottom pressure. So I'm a bottom pressure amateur. There is a professional there, Eric. Well, actually, Eric wrote a paper at the around 2019 to remind us how a long time ago we actually started talking about that. And a lot of stuff I learned from you. Thanks a lot for doing that paper. So we used outputs from Parker's smaller size model and my bigger model to look at coherence of pressure signal along. Did a lot of model data comparison. So basically, look at my set of slides as a kind of material for brainstorming. Really kind of trying to. It's nice to be able to talk to you, not just to myself about this. So, but it's not my full-time job to think about bottom pressure. So, we already have heard that in some sense, ocean circulation models provide useful information about bottom pressure variability. We also have heard that they're insufficiently accurate to just remove the signal from bottom pressure data. And it's not just because we are lazy and build bad models or use bad community models. Now you can all blame everything on model developers, right? But part of the signal, as Ken explained you, is not entirely predictable, not predictable at all. All those eddies in the ocean fronts, it's a part of the turbulent ocean, right? It's the analogy I always like to use is like try to describe accurately the billows, the smoke, the billows, right, from the chimney, right? So you can probably get the mean correct and statistics of the turbulence, but not exactly each individual eddy or billow, right? So and also we would like to use as a ocean circulation models. Actually, would like to use pressure bottom pressure data to verify our models, right?
Go down, right? Down exposed.
Oh, this. Oh, no. Okay, don't worry. I'll just press it. So I wasn't, when I was coming here, I wasn't sure how many of you kind of know by heart what those ocean circulation models are, and I just described briefly how one of those models is built. So this is the West Coast, kind of the dynamical base for the West Coast ocean forecast system, as we call it. So basically, this is the regional model. We kind of pick the piece of the coast. This is the West Coast plus a bit of Mexico, British Columbia here, and we do this on a 2-kilometer grid. So if you look on the right, kind of this is how topography bathymetry looks like. This is San Francisco Bay. We don't resolve very well. This is a 2-kilometer resolution with this particular case. These models are 3-dimensional, right? So basically, we also have discretization in the vertical. I showed 10 layers here for clarity, but we use like 40 layers. And they terrain following, which is convenient for to describe well variability in the bottom boundary layers and surface boundary layers, right? So, what we do on that computational grid, we integrate numerically equations for the sea surface height, two horizontal components of velocity, potential, temperature, and salinity. Using good, so that the science of how to do it went very far in terms of very accurate schemes. We also used vertical turbulence sub-schemes. So those are pretty involved models. People would like to build those community models and use them because they're expensive to build. So since it's a large size, but still limited area model, we need to provide boundary conditions. We provide initial conditions and boundary conditions from the global Navy state estimate. Also provide tides along the open boundaries, blow the winds, apply heat flux, and it creates quite a realistic representation of the ocean. Actually, we also have terrestrial discharge between like Columbia River, Fraser River as the Puget Sound. So I have run this model. Some of you know mean it as a data simulator. So this model, particular application doesn't assimilate any data. We run it just for, we can run it for 10 years, remarkably without big drifts. So, and the 10-year period includes, so it goes from 2008 to 2018, and it does include this period of 14-16 when we had El Nino along the west coast. And El Nino means a lot of things, but in particular it means like high sea surface height, and that like propagates like a Kelvin wave or total wave along the coast. So in this particular plot, I show the low pass filter. They use like 19-day low pass filter to show the sea surface, coastal sea surface height of La Jolla, California. Red is observations, and a thick black is the model. So you can see like this higher sea level 14-15. You also can see that the seasonal variability upwelling, downwelling, and the shades show the difference from in the model between our estimate and the model and the climatology based on the model, kind of seasonal cycle. So basically, El Nino corresponds to the higher sea level along the shore, the coast. That high level, by the way, then kind of part of that signal starts propagating to the Rossby waves offshore, creating positive anomalies further offshore. So can explain pretty well what's going on along the west coast. This is the image from the satellite at nominally like 2-kilometer resolution. See like a whole bunch of swirls and stuff. So winds blow in summer predominantly from north to south, create upwelling, create the current, and waters go offshore. They're replaced by cold waters from the bottom. That means like they're colder and saltier. That means like denser, right? And that does contribute to bottom pressure signal potentially, right? And now kind of everything starts going offshore. There's like Rossby propagation. There's a transfer to the edges, and sometimes I don't think one can actually separate those two processes. Wind is reverse of that in a sense. Winds blow predominantly from south to north. All those waters kind of pressed against the coast, and density. The isopeak one starts moving down. So that's it about the dynamics. Just to remind you. So, and I should try to use that solution to actually. A year ago, actually, I showed something from the solution using like this very long temporal filter, actually focusing on El Nino signal. And here I ran part of that solution, saving the fields hourly in attempt to kind of detect fields more carefully and look at higher frequency variability than it's like 90-day variability. So the bottom pressure is computed like this. So we have contribution. So you have the mean, you have contribution from sea surface height and a contribution from density. We sometimes kind of would like to call it baroclinic, but it's not always kind of means baroclinic because when your density is different from your reference density, so this term is also nonlinear. For instance, like on a shelf during winter, downwelling conditions will be nonlinear, even though the water column is mixed. So I pulled data from 3 sites, and thanks William and everybody in Eric for helping me getting this data, 0206. CE04, this data come from NSF Funded Ocean Observing Initiative, got it from their site. And these are the data I could find that are kind of at least longer than just a few months in the time series, and they cover this 15-16. I try to kind of look not just at the seasonal variability, I'll also look at the time when the sea surface height amplitudes are larger because of the El Nino effect in 15-16, right? So the black here is so it's all like data decided. Model is also decided the same way, and then you apply the 40-hour filter to remove any residual from the tide. So the black is the model, and this is the mid shelf, like 70-meter water, and red is the pressure data at the bottom. So I'm taking that this is like this kind of setting the basically the sensor drift as explained, right? But after then, kind of those lines follow each other remarkably well. So like in shallow water, the predictability is pretty well. And that's because the model of this class really responds well to the upwelling, downwelling, favorable winds. And in shallow water, like with water shallower than 200 meters, that's what you can expect. Over the slope, there is still kind of some kind of qualitative comparison, but also is not as kind of tight, and maybe not as tight even in deep ocean, but remarkably kind of the seasonal variability sort of is described correctly. I didn't apply like any long time filters here, so I didn't try to fit any of those.
Is there any data simulation in this model?
No, this model is just like purely fluid dynamical model, no data simulation. So just driven by boundary conditions and wind forcing and heat fluxes, right? So, but you can also see like the amplitude of those pressure, the pressure variability is quite consistent between the model and the data. And this is the deep ocean, and I'm the coastal ocean model. This is like probably the first time I ever looked at that deep. So we never care about what happens there. So really, we don't even have probably resolution to describe currents like around those underwater mountains correctly. So, but something is right there, probably, right? So, oh, by the way, so this gray area is in each time series plot I'm going to show. It shows like values between -5 and 5, -5 and 5 centimeters of the water column, right? So just so basically near the coast, the amplitudes are quite larger than offshore, and that's again like the kind of consistent with the basic structure for the coastal trapeze, for instance, right? So now what I do next, I take the same time series after there's no data here, just the model, and I ask myself like, okay, so as soon as those bottom pressure estimates for the model kind of make sense, right? So how much each of those two components contribute, right? It's a fair question, right? So and on the mid shell in 70-meter water, let me guide you through. So the total bottom pressure is black here, and the contribution from sea surface height is orange, and light blue is contribution from density. Right, so basically, it looks like over 70-meter water, the bottom pressure is totally controlled by the sea surface height. Right, so the contribution by density is not negligible, but remarkably, this curve is like much quieter. Right, it's like it's changing on a seasonal scale, but not on a day-to-day, not on a synoptic scale, which was kind of surprising, but probably somebody can explain this to me. So as soon as you get off the shell, this is 500-meter depth, right, in the bottom. So now what we saw there as black and red, kind of large important variability, now it's kind of dropped. It kind of basically the same curve, so kind of somewhere there near zero. So each of the components are quite large, in excess of like 10 centimeter, close to 10 centimeter of the water column. Sometimes, right? But those things are very well compensated. So the density part always compensates or nearly balances the sea surface height. So the question, like whatever is left, what drives it, right? So, and in deep ocean, same thing, right? Amazing signal, right? So I don't know what it is even, so I didn't have time to look at this. Why things sometimes can so abrupt so far. Probably that's the upwelling front is moved offshore. Maybe that's the eddy that gets there. So this is the curve, the same curve for the slope location, 500 meters. So and the same curves, except I add this dark blue curve is the observations, and they just like to show that again they kind of correlate the correlation between for the model derived bottom pressure and observed pressure for this period that's shown here is 0.51, which is different from zero, hopefully, right? Statistically, but certainly like sea surface height doesn't correlate with the full pressure at 500 meters. So that's what I want to see. Right, so now about this compensation, I kind of hope that previous speakers would cover that. And maybe I'm totally wrong here, but actually I'm not even physical oceanographer by training, so so kind of learn from books and from people like him. But when I came to Oregon State University as a postdoc, and I heard those presentations from the real oceanographers, guys who go to the ocean and do the samples of sample temperature, salinity, get density profiles, and from those they would create actually maps of just trophic currents sections, and that's all is all based on the knowledge that that's like on the assumption of the reference level of no motion that they would call, right? So which kind of means that somewhere very deep there's no motion. No motion to me means like no pressure anomaly, right? So, and that's what kind of happens in a lot of places, a lot of times. So we have a lot of edges in the ocean. This picture just kind of show you the progression of those trophic edges in the model. So those blue eyes is like those are cyclonic edges, counterclockwise if you look from the top in the northern hemisphere. So there is a dip in the middle, right? The negative pressure anomaly contribution, and that's what's compensated by the isopycnons that are uplifted in the middle. So they're so well sometimes uplifted that mixing in the middle of the eddy creates the cold temperature anomaly. So those eddies are usually cold eddies. So, all right. So if you look at the shelf, then whenever you have upwelling, you have a depression of the sea surface height near the coast. This is compensated by the high density, right? And downwelling in winter, same thing but reverse, right? So we have higher surface height, higher pressure from that, but that's compensated by the isopycnons that are driven down. So, right, like I said, like those people would assume like no motion, but we see non-zero pressure at the bottom. And I'm not, I know very little about deep flows really, but I just put this slide kind of to remind myself, first of all, that that's probably exciting area where we can look at some points. So we know probably so much about coastal flows, surface flows, but how much do we actually know about flows around actual volcanoes? So I bet there are papers, there are measurements, and I don't know the literature, but I still like honestly just say like this is exciting area to me personally, partly because of the ignorance on the field, maybe. So, for instance, like what drives these flows, right? So it's no direct wind forces. So probably they driven by kind of tidal mixing, by tides, tidal mixing, and maybe inertial energy from inertial oscillations that coming from the surface to the bottom. So also what I did, kind of try to look at those time series flows. Now again, this is just from the model. Red is the full bottom pressure. This is at the location of the slope again. Kind of trying to kind of make sense of that as a physical oceanographer. We actually see some episodes where surface height part of the bottom pressure is not compensated sometimes. And I look at that very briefly, and that looks happened when the front moves offshore and then retreats. So for some reason, I don't know why it didn't compensate, but kind of you don't find those very often, but this is how it works. But if you look now at the red, the total bottom pressure, so you kind of see like this is June, July, this is 2015. So basically over the months, the total pressure would kind of go by about equivalent 10 centimeters of water column. And that's mostly driven not by sea surface height, it's mostly driven by changes in the density, right? So we would like to associate it with upwelling, I guess, right? And when the relaxation from upwelling happens, like from July to September, it's also driven by density, which kind of says that if you want to do bottom pressure correctly on a slope, you have to build a model that does the density structure correctly. It's more important maybe than sea surface height, right? So one last thing. So this is like something, well, something we usually throw away, but at least there are at least two people who are interested in tides here. So just when I was trying to kind of clean up this data, this is the original 100-second temporal resolution record from 2006. It does look like tides mostly, right? Especially like starting April and May and June, right? But in winter it's kind of much more kind of noisy by eye, right? So and if you apply the filter that removes tides and everything that longer period than tides, right? So you're left with something like this, right? And I tend to believe this is, again, like this is something that's probably not very important for seismology at all, right? But it's just like you get those records, and sometimes there are things in them that kind of drive your curiosity. And so that noise that is left, that's noise on scales faster than tides, kind of have more of that in winter, and in the summer you don't have it, right? So, and I think, by the way, this is for the shelf sensor, so you won't find that thing in deeper locations, but in very shallow locations, like 70-meter water. I think this is the effect of the surface gravitational waves, even though the record doesn't resolve the individual waves, but it kind of has Alias representation, like by once every 100 seconds. And if you kind of find some data for like dominant, significant high dominant period, so those winter waves, not just higher, but they are longer period, and that's what kind of why the bottom feels them better, right? So if you try to actually apply a very simple linear theory for the constant bottom, this period translates into this wavelength, and you can even compute the bottom pressure of about 4.38 decibars, and so on. So not inconsistent with what we get from here. So I think those are gravitational waves. Lastly, so we are coastal ocean modelists, would like to provide those fields. If you guys know how to use them, would like to collaborate. And West Coast is not the only place where our interests extend. So we are having the model for the entire Bering Sea right now, 2-kilometer resolution. So if anybody is interested, especially for the whole Aleutian arc here, beautiful. So also this is the example of this is based on ROMS, and I built this. This is collaboration with Oregon State University with Skłodowski. And this is another example. This is the model that's based on the triangular meshes, the three-dimensional model called Schism. And my colleagues at NOAA and Charles Seaton at Columbia River Intertribal Fishery Commission in Portland are working to test this model. Kind of, the main focus is storm surge, but it's also three-dimensional model. And this is the main. Basically, resolution is variable from a few kilometers along the slope to whatever, 10-20 kilometers. And I think I'll stop here. This is some conclusions, and I'll use my time to take questions.